Oh, was or like
So they fire.
Oh, yeah, maybe.
Really?
Yeah, maybe. I wasn't expecting them like for the guy. I was actually literally dropped down right there.
Yeah, I know. I was smart. I was pretty sore. I couldn't do it.
So impressive.
Yeah, it's a good part.
Good morning, ladies and gentlemen. How are we doing today? Wonderful, wonderful, wonderful. Get logged in. JoinPD.com. There's your code. Get logged into the Pear Deck, ladies and gentlemen.
My phone was actually charged today. Don't die on me. Like it always does. Bonjour. Jasmine. Kim Azul. Kim Mays.
All right. All right, ladies and gentlemen. All right, so today we're going to continue. We need to get through Avogadro's law. We will probably get to combined gas laws today as well. The three gas laws that will be on your quiz on Friday are Boyle's, Charles, and Gay-Lussac's. Those are the only three that will be on your quiz on Friday. You will have to work a problem for each, and then there are three questions that are non-problems. So hopefully today's Pear Deck will help you get ready for that. Questions? Wonderful. So here's your first question. Gas law that holds temperature and amount of gas constant. Take your cursor, drag it over the one that you think it is. Which one holds temperature and amount of gas constant, ladies and gentlemen? Drag your icon onto which one you think it is. By the way, if you can't do this, you're going to be losing points on Friday's quiz. All of these should be in the exact same spot, which they're not. But those of you who had it on Boyle's law, you were absolutely correct. Boyle's law relates pressure and volume, so temperature and amount of gas are held constant. Wonderful, wonderful, wonderful. Gas law relating pressure and temperature. Which one has pressure and temperature being changed? Well, at least we're split between the two that are possible answers. Pressure and temperature, ladies and gentlemen, that is Gay-Lussac's. That is Gay-Lussac's. Volume and amount of gas would be held constant. Gas law that is a direct relationship. Gas law that is a direct relationship, ladies and gentlemen. All right, so the gas law that is a direct relationship, ladies and gentlemen. All right, there you go. Charles and Gay-Lussac. Actually, we'll learn about Avogadro's today. It also is a direct relationship. So the only one that you couldn't have picked was Boyle's, ladies and gentlemen. Boyle's. Gas law for why helium balloons shrink when you go outside with them in Wisconsin winters. Which gas law is the one that tells us why helium balloons shrink when you go outside with them in Wisconsin winters, ladies and gentlemen? Josh, which one? It is not Gay-Lussac. It is, what the heck? Charles. Charles law. Charles law. Final question, ladies and gentlemen. Gas law that affects when blowing up a balloon. Gas law in effect when blowing up a balloon. This one you have to use the process of elimination for, ladies and gentlemen. Think about what happens when you blow up a balloon. Actually, we've actually introduced this one, so no, you don't have to. All right, who's got it? Nope, not Boyle's law. What happens when you blow up a balloon, ladies and gentlemen? Explain it to me. Come on. Your juniors, sophomores, juniors, and seniors in a high school chemistry course. What happens when you blow up a balloon?
The volume.
It expands. Why?
Because you're adding more air into the inside of the balloon.
Okay, so which variable is adding more air? What? No. Volume is the amount of space it takes up. Which variable is adding more air? Amount of gas. So which one does it have to be?
Avogadro.
Why?
Because it has amount of gas and volume.
And because all of the other three, Boyle's, Charles, and Gay-Lussac's, what are you required to hold constant in all of them? No. What are you required to hold constant in Gay-Lussac's, Boyle's, and Charles' law? There's only 4 variables, ladies and gentlemen. No. Temperature changes in Gay-Lussac's, temperature changes in Charles. Pressure changes in Boyle's, pressure changes in Gay-Lussac's. The amount of gas. Which one is the only one that doesn't hold the amount of gas constant? Avogadro's. Avogadro's is the only one that does not hold the amount of gas constant. Okay? The only one. Questions? All lefty, ladies and gentlemen. Now, take out your packets. You're not going to believe this, ladies and gentlemen. Somebody yelled at me yesterday. A student yelled at me for deceiving them. Because yesterday, when we gave you our gas laws, which was the first gas law we talked about yesterday? We talked about Charles, right? But in the problems, which gas law is first in the problems? Gay-Lussac's. Oh my God. Mr. Brand, you can't change the order of things on us. Well, I did. Okay. By the way, up at the top by Gay-Lussac's law, I would write the following, ladies and gentlemen. P1 over T1 equals P2 over T2. Now, I would also probably somewhere write this. What are the units of pressure? Give me one. Give me 1 unit of pressure, Irving. PSI. Stephen, give me another. MMHG. Ariana, give me a third. ATM. And then what is the last one, Eric? KPA. So if you see one of these units by a number, it has to be describing a pressure to you. Has to. Okay? What are the units for volume? Faith, give me one. Milliliters. Good. Jack, give me another. Liters. Give me a third one, Caden. Centimeters cubed. Thank you very much. Those are the units that I will give you. Okay? So give me a unit for temperature. Give me a unit for temperature, Jasmine. Degrees Celsius. Give me another unit for temperature, Jaden. Degrees Fahrenheit. Give me another unit for temperature, Skylar. Calvin, thank you very much. By the way, we'll never give you one in degrees Fahrenheit. Haven't shown you how to convert it into Celsius. Haven't shown you how to convert it into Kelvin. I will never give you one in degrees Fahrenheit, but you are correct. That is a unit for temperature. All right. N. What is the unit for amount of gas, Christopher? Mole. Now, technically, it is not the unit for amount of gas, but what other unit could I give you that you could easily get into moles? Oh, how quickly we forget the last unit. I wouldn't do that because it could confuse you here. I'm already giving you volume. Mass. What's the unit for mass, Shenza? Grams. I could give you the grams and tell you what it is. We could convert it into moles, correct? So those are the basic units that you are going to use in this unit, ladies and gentlemen. Now, when you get to a problem, ladies and gentlemen, ask yourself this. What is that number describing? 10.0 liters. What is that describing, Joshua? 10.0 liters? That's a volume. So maybe make a note for yourself above that number. What is 0.889 ATMs? What is 0.889 ATMs, Pierce? What is 0.889 ATMs telling you? It's a pressure. 15.0 degrees Celsius. Morgan, what is that telling us? All right. So I've got 3 variables here, right? Now, I haven't even read the problem, but I already know what a volume is, what a pressure is, and what a temperature is. Now, what is the title of this page of problems, Josie? So which one of those do I know I'm not going to need? Christopher? Volume. Why? Gay-Lussac's law problems don't involve a change in volume. Okay? Don't involve a change in volume. So if I put a change in volume problem in here, I either put it in the wrong spot or I messed up. I didn't mess up. So that tells me this is not going to change because it can't. And if we read along, it says assuming no volume changes. It didn't change. Why did I give it to you? Well, to see if you would try to put it in somewhere, okay? Or to see if Angel would go ahead and hit Christopher because he's mad at him for some reason. I don't know why. But anyway, ladies and gentlemen, so it can't be volume. What temperature is needed? Wow, that's like asking you a question. My guess is T2 is what we're solving for because it's asking you for the temperature. So I do still need one other thing to put this into this problem. What is it? I need a second pressure. But it doesn't give me a number, does it? But what does it do? Pressure is doubled. Now, not very often will I do this, but if we say that pressure is doubled, you should be able to figure that out. Because what it means is the pressure that we had, take it times 2. So take this pressure here times 2. P2 equals P1 times 2. Now you can do this problem, ladies and gentlemen. Now you can do this problem. Okay? You are always, always, always able to find 3 out of these 4. If you can't do the problem. So, here's a P, here's a T, here's a P2. I can plug it in, and I'm solving for T2. Okay? You've got 20 minutes to work on problems, ladies and gentlemen. 20 minutes that if you need my help, you are more than welcome to raise your hand, and I will come over and I will assist you. 20 minutes to get things done before your quiz on Friday. This is the last day in class that I will guarantee you time to work on these problems before your quiz. Now, I'm here after school today. I'm here after school tomorrow. I get here at 6 o'clock tomorrow morning if you want to come in and see me, ladies and gentlemen, to get help on these. Okay? The one thing I can't do is I can't help somebody who doesn't tell me they need help. So, 20 minutes, clock is running, get done what you can, have questions, raise your hand, call me over. I don't care if you're going back and work on this as one big group, but let's get some things done. Okay? Go to work. Go to work, go to work, go to work. I need to pick up these 3 pieces of paper, and then I will be around if you have questions.
We're gonna assume that it's 576. Oh, yeah, I lied. Wait, no, that's the wrong one. I was gonna say. Oh, I was right. Oh, no, I was right. I got this right, so I got 576, and then I put it back into Celsius, so 270.
How does that look?
Now we can do it, right? Can we use column
Yeah.
because we have to take 30 degrees Celsius.
Chenza, come on.
Do we need to care about secrets?
Well, we always need to care about sig figs in a final answer, yes. But here's what I will tell you. When you look at a problem like this, 3 sig figs, 3 sig figs, 3 sig figs, what's your final answer in?
3 sig figs.
Because you're multiplying and dividing, it makes it easier for your sig figs. Look at how many are in each number. Your final answer needs to be in that same number. There you go. Okay? By the way, I might have mentioned this once or twice. 90% of the time, your final answer is going to be in 3 sig figs. Okay? So it's not something I would worry about, but if you have time to check, I would check. Yes, sir.
Why do you? Yeah, and then you'd have to put it back into.
Why do you flip?
Okay,
And the
because
big,
when you are solving a problem, we need to isolate a variable. Okay? So can I make it in here a little bit, please? All right. So our formula is P1 over T1 is equal to P2 over T2. Okay? The problem comes when we're solving for T2. It's on the bottom. We don't want to accidentally solve for the reciprocal. So we do cross products are equal.
Kind of one of those.
Okay? So like in math, cross products are equal. Okay? Now because of that, then if we're solving for T2, we divide this by P1. So what it ends up being is P2 times this side flipped over. To mathematically isolate T2.
I did do it right.
So that is just the math of doing this problem.
So when
It
you
ends
add
up
it,
this way. It
15
ends up with this being flipped over because we're
270,
bringing it over to the
because
other
15
side.
is our original
Okay.
temperature, and if
Now,
you want to get
again,
it to Kelvin,
you don't need to
have
show me
add to
anything.
73, and
You just
that's
need
how
to be
you
able to
got
do the math to get
570.
the correct answer. If you were to accidentally solve this and end up with a number like 1 over T2, reciprocal key on your calculator and that'll flip it. You can still
Oh
solve
wait,
it.
oh,
It doesn't matter.
or wait,
But what
that's
you have to
76
recognize is, okay,
plus 15.
if I solve for the
No,
reciprocal
wait,
of this, if you were expecting your number to get bigger, it's probably gonna get smaller. If you're expecting your number to get smaller, it's
How do I
gonna be
get-
bigger.
Because I'm
So
assuming
that's what
we
you
don't
gotta
make
see.
this, so I don't get that. And
By putting it all on one line like this,
then you get
okay,
that answer.
then it looks like a Boyle's Law problem and what we've been doing.
Point, oh wait, hold on.
But I need to at least introduce it to you this way because that's the way it's
The
supposed to be.
1.778 just comes when you multiply this by
So
2.
all
because
this is
it
just a
says,
math.
so what
You
temperature is
isolate
needed, so that's what we're trying to solve for.
If
For
it's
the pressure to
P2
double, and then this was our like original pressure.
that we're solving
So
for,
we doubled it,
we
and
don't
that's
have
how
to
we
do
got
hardly any of that. We just take this
our
side
second
times
pressure.
P2.
So P1.
What we do to one side, we do to the other.
So
And P2 equals
Wouldn't you wanna
T2
do this
times
down?
P1 over
wait,
T.
wait, 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 wait.
Why? Because this was on top. I didn't have to flip these. I just needed to take this T2 and get it over to the other side. Okay? So that's just mathematics so that we can solve this equation. Okay? So that's why it happens.
Times
Again, I don't care how you want to do your math as long as you do your math correctly. Okay?
Okay, that's not right.
Much better.
So we did multiplication for that then?
You can get
Yeah.
you. Let's say the key.
No?
Sir.
Oh my god.
Wait,
How did he do that?
Yes.
Where did that come from?
he said something about make sure not to multiply it by the reciprocal. So I think we would have to flip them because I think the temperature should be on the top. So I think
Oh my
instead-
gosh, there's a Boyle's Law in there! Shenza found it! Number 7's a Boyle's Law. Do Boyle's Law. Sorry.
Oh, so we can burn that.
Sorry. 7's a Boyle's Law. Do Boyle's Law.
No.
What?
No. What?
Oh, see, I'm so smart. Told you.
Solve for P2.
But yeah, but where does that come from?
From when you double this, when you literally just multiply it by 2 because our pressure here doubled. Sometimes we just have to read the problems. I actually did not get it at first. I'm gonna be honest. I did not get it at first because I was confused. I was confused if temperature needed to be doubled or pressure.
I'm not excited for physics.
What?
It's harder than this.
Wait. 15 plus 273.
That's what I was asking you. Like, I don't know how.
Oh, that's how I did it. Look, listen, I'm dumb. Listen, I'm dumb. So I guess you could just ignore this too. Like, ignore all this because look, I don't think he would want you to. But look, so you know originally how you said 15 plus 273 equals 288, but we doubled it. So
that means P2
yeah.
That's so stupid.
God, I'm such a genius.
Oh,
Maybe we should become
I
famous
don't
one
think
day.
it'll
isolate this.
No, it probably won't.
Probably just this one.
Zero.
Probably just getting my
We do
hopes.
one side, we do
And
the
then-
other.
Well, the
So-
guys in this one just
But you're gonna get your answer completely wrong. Why?
to get
Somebody tell him why he's gonna get his answer completely
to
wrong.
get temperature.
Answer. Tell me why you got your answer completely wrong. Yeah, on number 6.
Yeah,
We're gonna get it wrong. We're gonna
Wait, X. Oh, X's are variable. No, Calvin is our variable. So he just uses X as his.
Well, because what is the one
X
thing I told
equals
you about
the
gas
answer.
laws that involve temperature?
Why can't he just put Calvin?
What? To Kelvin. Did you convert to
Why
Kelvin?
can't we just put? Why can't he just put? Oh no, that wouldn't actually fix it. Oh, okay, yeah.
We're
I'm
both,
confused.
okay, sorry. My bad.
I'm moving on to the next problem.
Okay. I
Moving on to
I
bigger
looked at
and
this.
better things.
This wasn't going to work out. You confused me by putting it in here, but as long as you're doing it that way, that's fine. But understand, in a problem on a test, I need to see where these were converted. So
My
doing
two
this
CCTV
is okay,
looks so
but
good
you
and that
can't like
looks so
eliminate this step and just give me an answer without showing me that. Does
But
that make
that's-
sense to you? But otherwise, yes, I'm sorry, I only looked at here. Do it in Celsius and that would bring it.
So pressure.
Right? Okay? Well, that's what you gotta figure out, because again, that's something that I gave you a while back.
P2 on both sides.
Yeah. See, this is what you gotta learn some of this stuff. Where's your
What
periodic
do we
table?
add?
In my desk. So it's not that you don't have it, that you're too lazy to don't have it. Okay,
I think
good, just so we're
the
clear.
gist of this one is to probably ignore this next 10 because it just asks will the temperature at 910 degrees Celsius. I think that's what we're trying to figure out.
I'm trying to figure out.
Oh.
So we could
Okay, so you solved for T2? Well, I don't either. This problem doesn't have anything to solve. Now, I don't know where you got this number from.
Most of the song.
Okay,
yeah,
why did you multiply that by two?
What?
yeah you. So,
What the?
you go.
What's the answer? Okay, well, somehow you would have to explain
It
this.
was,
here
it was
because right now
like,
you-
mitosis.
That answer is kind
But
of- Normally,
yeah,
that
it's-
formula, there, T1 over T1, T2 over T2, there'll be some variable.
You just don't
Wait,
Which one? Now, you just,
what
you didn't put the variable in there, you just solve for it.
pressure?
Not every
8.4.
problem is that easy though, where
It's
it's
a
a
first-
double. Okay, sometimes it's going up
no,
0.63.
sorry. Oh, something.
Well, listen, the pressure goes up to 0.63, so does the temperature, but it's not, you know,
All of it.
A tinkle
it's not as easily seen as just double, so this should double.
So I'm assuming that probably be the second.
What's that?
But it originally has a pressure of
Right, so
8.4.
what do you got?
Okay.
Okay, we need something on the other side. I either need a pressure or a
30 plus
temperature. What do we got?
3 times
Okay, then put the pressure in here, and figure out what the temperature would be. Yeah, yeah. You can do
It's
it
going
either way.
crazy right now. Don't get notifications blowing your screen.
So then this one.
Okay, now, here's the thing about this problem. It doesn't really care what this new pressure is. What it wants to know is if this new pressure
Converting the 30.
is more than this number.
Yeah.
Because if it is, what will happen is we'll add it.
So
That
3
would
of
If
3
it's not more than this number, what will happen?
equals.
So you could, now when you solve this, you're gonna go back and compare this to that number. You could have also put the 47 in up here and found out what temperature that tank would burst at.
I don't know.
And then compare this temperature.
You want to write it
to the
down.
temperature you got. And again, the same reasoning that you just did, you would be doing here. Okay?
Yeah, where did you
If this pressure is the temperature at 909 degrees Celsius, is that tank gonna burst?
Wait.
Or do you? Oh, wait.
Is this over 909?
How do we know?
I understand. Eventually, you could convert it back to Celsius and compare it to this number. You're gonna compare this number that you get here to this one.
Oh, you do 273. But why did you do that? Oh, that's our second temperature. So, and to put it to Kelvin.
How do you want to do this? You want to do this?
I got it. Everything.
My suggestion.
Oh, the rest of the everything in Guy Lusak's law is whatever the temperature. If you see a temperature, it's automatically Kelvin. So if you ever just see the temperature, just put it, add it to 273. And that's how you get one.
You can't subtract it. You're not adding it.
So then now, so
Well, you get that one in full different
I did
way.
it.
Because like this one.
What you do on one side of the equation.
Just take a.
I know that I think I'm cooking, but
I don't care how you want to do that. But that's
and
all
then
that is.
yeah, you get this. Like that's what I got. Because what?
Yes.
You
You cannot. And I want the
Because you're doing
credit.
anything.
I need this.
She did what I did last year, but they wouldn't let her.
I'm confused on where.
It's just
Okay. What do we do to solve this? You'll never go wrong if you do the process. You'll never go wrong. But there are other ways of solving this mathematically.
You're in part A right now?
I
So I'm going to take this out of scientific
failed
notation.
last year because of my
Oh,
So now you're in part B.
next year.
It's only gonna get worse.
I'm supposed to be in pre-calc.
sure.
Yeah. It's okay. I took the same class.
Now, how do I get X?
Do the same.
I'm sorry.
I took you all those black predictions yesterday. And then I
You divide that one. This number on both sides.
So I'm hoping.
So now,
yours.
now, all you gotta do is do that next.
Oh, I'm at 2.9. Well, just kidding. Yeah, but I actually just, I don't know, I stressed out so much in this suckers.
And it's a what?
Last year, I was cried when I went 100%
Temperature, what you convert it to Celsius.
Well,
I
it's,
got it back to you.
Convert it to Celsius.
what's this card thing? Do you have it first?
That's true.
I don't know this one.
I saw Danny walking into her class today. First thing in the morning this week.
Everybody hates her. Well, I do.
Yeah,
It's
you know why.
I do know why, but she's nice to me.
I'm gonna have to write this.
Small amounts.
She likes me. She gets me.
Oh,
It's really funny because he does nothing, but he fell asleep in her class.
this is
And then the individual.
this is what you're doing right now.
No. 910, that's the temperature we got it up to.
This is what you're doing right now to this card thing.
Well, not first. It all depends on how you're looking. If you could solve for
You
pressure,
are insane.
bigger than this, less than it would.
Bro, that looks so I look really doing
Both the
something.
temperatures will.
I know there's a
It won't.
Wait, please.
That's yes, sir.
I don't want to see.
I'm not worried about that. I'm not worried about that. You and me we're gonna be off by a little bit depending on rounding and things like that. I'm worried about, did you get 21.6 6.
On TikTok.
It's now,
On
we're not off
TikTok,
by a round.
glazing is when
Something is wrong. You know what I mean? So if you're off by tenths, hundredths, even if it's a big number, maybe
Yeah.
ones place,
Sounds a little
not a
bit.
big deal.
No, I'm just kidding now. I'm kidding now. I'm kidding.
Because I literally nothing at this moment.
You hit her.
That's then you're the same shit.
No, I know. Yeah, he tells me.
So now we need to
Oh.
eliminate.
Poor Dan.
My suggestion.
It's like a version of you.
The reason we
Yeah,
do
like
that
like
is
dancing
now we'll
part
because everything's
because I feel like if he doesn't get something right this time or the second time, then we just start stressing out. And I was like, maybe the working was in the cash. I feel like this is just sweet. This is weird. This is for you.
I was supposed to be in the
This is fun though. Use your Mario jump or your
We're gonna take isolate this. And if we do this, it makes it easier for you to see that. Again, how you do the math is completely up to you. The main thing is that make sure that
Keep playing games.
yes. Did I change that
answer
answer? I didn't realize it was Boyle's Law.
So is it?
Is that right then on the answer sheet?
Who, Joey?
What would it occupy?
No, it is, this is correct.
Is it like the
It is-
same shit?
I shouldn't have put it
Nah,
into
man,
this
he doesn't
section
know
of the
it to me.
worksheet, that's
Okay.
it.
Like no one's like
No,
Jen gets,
nope. So if you got the same
Not a
thing
lot of
that I'm
guys,
getting here,
but I'm just
Okay.
saying.
so
We're doing this
again, in a little while,
it's
I'm
like
gonna
very
give you
big
problems
stuff. Like, I'm not
that are not
gonna lie.
broken down by, you know, sections, you're gonna have to figure out which law to use.
Is that 2 points?
So it comes down to which of these formulas should
That's
I
the
use. Okay.
no, it's for
So you always go to count.
All right, ladies and gentlemen, you got 3 more minutes and then we're moving on for today. So if you have questions, please ask. Yes, sir.
well, why don't we just come in at 6 in the morning?
Combined?
Yeah.
No, nope, as far as gotta do section
just-
trials, that's it.
When you just cancel these out, so you multiply 183 times
Yeah.
8.0
Yes,
I mean times 8.4
questions?
divided by 303. And it should
Well,
be
I'm not either, but I hope you're doing your math correct, because if not, you're not gonna get the right answers.
303.
Okay? You've also got the answer keys, you can check, let them
So
help
I
you
guess
work
when we're
through
just trying
things.
to find the temperature, just multiply by the reciprocal. And you know you're gonna be good.
If you're arguing over 202 and 2020, it sounds like you guys are off by a factor of 10, maybe when you put something in or out of scientific notation. So check the answer key, see which one it is.
Oh,
I did get it right, right? Wait, so that's 36, and then we 36.
So I get to do is details like this one. But sometimes it's
It'd be really funny if I just came in
not even.
and
Should they always go together?
He's just kind of crazy. Yeah. Tell me. Tell me. You have to put up with you every day. In this class. Just kidding. You have to put up with you during the lollipop. That's loud. You have to put up with the fact that it's every second. We have to do it again. I'll probably do better.
All right, ladies and gentlemen, have a seat real quick, please. I'd like to explain a couple things to you. We'll get into Avogadro's law, and then we will talk about combined gas laws. walking around, talking with a bunch of you. It is not your science that is killing you. For some of you, it is your math. Okay? Now, this is not a math course, but you need to apply a certain amount of math to these problems. The first problems we did were Boyle's Law. The nice part about Boyle's Law is because it is an inverse relationship, because it is P1 V1 equals P2 V2, it is very easy to isolate a variable when things are like this. Pick a variable, Maddie. I don't care which one. Which one or two? Okay. So if I'm going to isolate V1, ladies and gentlemen. Now again, when you have all your numbers in here, this will be the only thing that is a variable still. But how I isolate the variable here is the same whether there are numbers in there or not. I'm going to take this side, and because V1 is multiplied by P1, I'm going to divide it by P1 to get rid of that and isolate the variable. Get V1 alone. Mathematically, if you do something to one side of an equation, you do it to the other to keep it equal. So since I divided this side by P1, I'm going to divide this side by P1. So V1 equals P2 times V2 over P1. Always. That is just the math of it. Okay? But it's easy because everything is on one line. When you get to when you get to Gay-Lussac's or Charles' law, P1 is over T1 now, and P2 is over T2. Now it isn't quite as easy to do. The easiest way to solve that problem is to make it look like Boyle's law. And we're going to do what they call cross products are equal. In other words, the number on top on one side and the one on the bottom of the other get multiplied together. So this becomes P2 times T1 is equal to P1 times T2. Now it looks exactly like Boyle's law did. Pick one that I'm solving for, Faith. T1 or P. I'm sorry. Normally we'd either be solving for T2 or P2. Pick one. So let's solve for P2. To do that, now we're going to do just what we did up here. I'm going to isolate that variable on one side of the equation. That means I'm going to divide this side by T1. I'm going to get it alone. But what I do to one side of an equation, I have to do to the other. So now P2 is equal to P1 times T2 over T1. Okay? All that is math, ladies and gentlemen. That's all that is. Isolating a variable, solving for it. Yes, I'm sorry, you have to use math in science. We give it meaning. Because now we're not just talking about finding X. X has a value. X is something. It is a pressure. It is a temperature. But we're still just solving for X. Okay? Questions? Again, I can show you these things. I can help you with them. But unless you're going to practice them, you're not going to get better at them. So I got no problem with you using the answer keys. I don't. But if you're using the answer keys, please try to do it on your own first. See how it works for you. Yes, I messed up. I put a Boyle's Law problem in there for you. I'm sorry about that. But all you need to do is use Boyle's Law formula up here for it and solve for it. You've already done that. You should be able to. Okay? Questions? All right. Let's talk about Avogadro's Law here. This is not going to take long, ladies and gentlemen, because Avogadro's Law, we've already introduced to you. We introduced it back when we introduced the mole concept. And we said that at STP, 1 mole of a substance always equals what volume? 22.4. Excellent. Here's the problem. That ain't true anymore. Because we're not at standard temperature and pressure all the time. We are not at standard temperature and pressure all the time. But there is still a relationship there. There is still a constant. And Avogadro's law, just like any of the other laws, says that the volume of a gas will vary directly. What kind of relationship? Direct. To the amount of gas. In other words, the more gas that you have, what happens to your volume? It goes up. Think about blowing up a balloon. The more air you put inside of it, what happens to the balloon? It gets bigger. That's Avogadro's entire law, ladies and gentlemen. Hey, you put more air in something, it gets bigger. Okay? Because we can't change what? We can't change temperature, and we can't change pressure. So the object has to get bigger. If it didn't get bigger, what would change? If you put more air into an object and it does not get bigger, the volume does not change, what else has to change? No. Think about pumping up a tire on a bicycle, on a car, on a volleyball, on a football, on a basketball, on a soccer ball. You put more air into it. There is a limited amount of space, right? What happens? The pressure goes up. All these things are intertwined. All of these interact with each other. There is no law for pressure and amount of gas. There isn't. But hopefully you understand, you put more air in your car tire, the pressure in the tire goes up. Avogadro's law, volume and amount of gas are directly related. Which means, ladies and gentlemen, V and T are in a direct relationship. P and T are held constant. And V1, or V over N, equals a constant. Now at STP, what is that K? What is the volume of 1 mole of a gas at STP? 22.4 liters divided by 1 mole equals 22.4. That's the constant. But it only works at STP. You change STP, that constant will change, but there will still be a constant. So guess what? V1 over N1 equals V2 over T over N2. By the way, this will be the least used gas law that you will ever have. Ever have. But we introduced it to you. Because what happens if we double the amount of gas at STP? The volume doubles. So guess what happens to the volume if we double the gas and you're not at STP? It still doubles. It just may double from 20 to 40 instead of 22.4 to 44.8. It still doubles. If you cut it in half, it's still cut in half. It is still a direct relationship. Okay? So, 2.36 moles of gas is under a condition that has the gas occupying 120 or 1,256 milliliters of space. The total number of moles in the container is increased to 0.825. How much space would the gas occupy in liters? Again, assuming no change in pressure or temperature of the gas. Here's our original moles. Here's our original volume. We increase the moles. What's going to... Wow. I did that completely upside down. Completely upside down. I don't know why I did that way, ladies and gentlemen.
You should have made a mistake.
I shouldn't. You're right. Somebody else must have typed this up for me. Shenza, did you type this up for me?
Yes.
Okay, good. Thank you for taking one for the team. Because that ain't even close to being right, ladies and gentlemen. Holy cow. Shenza just earned an A for the class by taking one for the team. That's awesome.
Yes.
Gotta help me here, ladies and gentlemen. I need you to do some math.
I'm doing it.
You're doing it?
No, not that far.
What? Okay, that looks better. Now. Whoop. Here's the good news, ladies and gentlemen. I didn't completely mess it up. I just semi-messed it up.
You didn't mess it up.
Shenza did, I know, but I won't blame him much for this. All right. All right, let's try this again, ladies and gentlemen, this time with the right things there. V1 over N1, volume, number of moles. Moles increase, what's going to happen to the volume? It's going to increase. By the way, the moles went up by about how many times here? About 0.2 to 0.8. 0.2 to how many times though? That is 0.6, but how many times larger is that? About 4 times. So I'm expecting a volume that is about 4 times larger. So 4 times 1,000 is what? What do you know? We got an answer that's right here. Okay? Again, take everything. I don't care how you do the math. You got to get your math done. You got to get it done right. Put it all on one line. Isolate your variable, your choice. But Avogadro's law are no different than Charles or Gay-Lussac's law problems. Questions? Let's see what I did to the next one. I'm almost afraid to ask. Oh, good. There was only one.
I wasn't finished. Thank you.
No, what did I do? Spell combined wrong?
Huh? No.
The next slide says combined gas loss. What did I get wrong on it, Shenza?
I type all the slides, so I'm glad I didn't make a mistake.
You only made one.
Yeah.
Now, I only made one too, but you know what? 26 years later, I'm still married, so.
Yeah.
You're him.
I'm kidding. I also have 2 kids, so I can't really say I only made one mistake.
You're him. He's that guy.
Are you done?
Yeah.
Can I go to the next slide?
Yeah, I was just complimenting you
On what?
on you being that guy.
I am that guy. I love my wife and children. If she ever asks, you tell her I said so in class.
God,
No, I was just listening.
Okay. Now, combined gas laws. Combined gas laws came about because what are the chances of always holding 2 things constant? Not good. Sometimes 2 things are going to change instead of or 3 things are going to change instead of just 2. So now we have what we call combined gas law. Now, you want the good news or the bad news? The good news, you can use combined gas law on every problem we have worked so far. Instead of using Boyle's, Charles, and Gay-Lussac's. Okay?
So there's no bad.
No, the bad news is it's a little bit more difficult law.
Oh.
But if you remember this one, it takes the place of those 3. Here you go, ladies and gentlemen. Combined gas laws deals with changing 3 variables. Pressure, volume, and temperature. So what's still held constant? The amount of gas is still held constant. Okay? Where is pressure always in every one of our formulas?
Top.
Where's volume? And where's temperature?
On the bottom.
There it is. P times D over T still equals a what?
K.
What's K?
The amount of.
No!
Wait.
A constant.
Yeah. That.
It still equals a constant, ladies and gentlemen. So guess what? P1 times V1 over T1 equals... Very good, Eric. Very good. Very good. Now, I just told you that you could use this law in place of what? All of the others. And here's why. Let me explain. What's held constant in Boyle's law besides the amount of gas? Temperature. So if you have a problem, what's going to be the temperature here? Now, if you were doing this in math, oh my gosh, math again. What would be the first thing you do to solve this problem? Raise your hand and ask for help. Okay, good. Second thing you would do. Cancel out what? Sorry, I thought it was you, Maddie. Morgan, sorry. These two are the same, right? Exactly the same. If you're doing exactly the same thing on both sides of an equation, what do? You just don't do it. You get rid of it. Oh my gosh, what gas law are you left with? That's Boyle's law. That's Boyle's law. So what if you were multiplying this side and this side by the exact same pressure? You take it out. What are you left with? You're left with Charles' law. There's Charles' law. And what would happen if the volume didn't change? You're left with Gay-Lussac's law. That's all three of your gas laws right there. And you know what? If it confuses you to say, you know what, I'm canceling out the same number, do the math. You're still only going to have one variable out of all of this. One variable. Solve for it. Solve for it. Okay? Solve for it. But again, because you have things on top and the bottom, what's the easiest way to solve for this? To do what?
Nice.
What? Do math? What kind of math are you going to do? I guess it's too much to ask. We were on a roll there of doing well. How about this? What did I just do, ladies and gentlemen? We did cross products are equal. Got it all onto one line. Says now you got three things there to multiply on each side. Doesn't matter. The only way you can solve this is if you only have how many variables? One. You can only have one variable here. So guess what? When you're done putting all of your numbers in, how many variables are you going to have? One. One. Now again, if something doesn't change, you can put the exact same number in on both sides. Go ahead, put the exact same number for pressure in on both sides. It isn't going to change the calculation, but you can always use this. Always. Always. And if it says something doesn't change, and you're like, well, what number should I put in if it doesn't change? What's the easiest number to put in, ladies and gentlemen? No, don't put in 0. 0 will make everything 0. But you can't use 0. Use 1. The volume, 1 liter. Put it in on both sides. Temperature, 1 Kelvin. Put it in on both sides. Pressure, 1 atmosphere. Put it in on both sides. Wow, that makes the problem difficult, doesn't it? Yeah, 1 times 1. Yeah. Yeah, anything times 1. Oh, man, what's that again? I can't remember. Okay, good. All right. Carbon dioxide gas is under following conditions. Pressure, 105.3 kPa. Temperature, 15.8 degrees Celsius. Whoa, wait a minute. We got what in these problems? Temperature. What? 2. Good. Can't solve these without putting temperature into Kelvin, ladies and gentlemen. Can't do it. Can't do it. Can't do it. 15.8 degrees Celsius and a volume of 689 milliliters. Guess what? Those all go together. Okay. Ooh, chicken butt. You're guessing what? And it's chicken butt?
Yeah.
Wow. Wow, wow, wow. Eric, I didn't think you were a chicken butt kind of guy. 105.3 kPa, Eric. What is that?
The first pressure.
The what?
The first pressure.
All right. P1, as we will call it. 15.8 degrees Celsius. What is that? Jasmine. 15.8 degrees Celsius. What is that? PTVN. Thank you. T1, as a matter of fact, ladies and gentlemen, 698 milliliters. What's that, Maddie? V1. All those go together. All right. 45.6 degrees Celsius. Angle, what do you got?
Wait, what was the question?
45.6 degrees Celsius. What is that? P, value, pressure, volume, temperature. He's calculating it on his calculator. That's telling you if it's a pressure, a volume, or a temperature?
I think it's for version.
No, I just want to know what that number represents.
Oh, T.
All right.
That's what I thought I heard.
Ay, como estás malito en la cabeza.
421 milliliters. Oh, man, who can I ask who won't mess this up right away so it doesn't take longer? Joshua, go ahead. This has got to be a V2. Well, which one don't we have?
P2.
So what do we got to be solving for? Oh, look, new pressure, P2. Now, you do need to read this problem. Why?
It's good to read.
No. Please read the problem and tell me what could mess you up here.
If the temperature is raised.
The temperature is what?
Raised.
It's raised that. It's not raised to that. It is raised 45.6 degrees. So what do we have to do with that number? 2?
273.
No, not 273.
Oh.
Add to
15.8.
Oh, it's literally right there.
Johnny.
Now, you are right, though, Caden. We are going to have to eventually get to Kelvin. But we need to add these two together because the temperature was raised that many degrees. 61.4 degrees Celsius, which we now add 273 to get 334.6.
Calvin.
Point what?
6.
15.8 plus
Oh.
45.6?
Womp womp. You did something wrong.
Okay. All All right, combined gas laws, ladies and gentlemen. P1, V1 over T1 equals P2, V2 over T2. So P1, 105.3 kPa. V1, 689 or 98 milliliters. Now, does it matter what unit pressure and volume are in? I love it. I love it. No.
No.
As long as what? As long as they're the same on both sides. I don't care what pressure unit we use. I don't care what volume unit we use. How about temperature, though?
Yes.
So what's got to go on the bottom here?
334.4.
Nope. Be careful. Not 334.
288.
We need to convert the 15.8
Oh,
plus 273. What do we get?
288.8 Kelvin. No naked numbers.
What's this equal to? All right. What are we solving for?
Second.
So P2 is going to be our variable here. What's our V2? And what's going to be our new temperature?
334.4.
Okay. Now, here's a question for you. What is happening to temperature in this problem?
Increasing.
What should that cause pressure to do?
Increase.
What is happening to volume in this problem?
Decreasing.
What should that cause pressure to do?
Decrease. Oh, no, increase, sorry.
Decrease.
Oh, it's increase. Oh,
I got people yelling both at me. Somebody make a decision here. What kind of relationship is pressure and volume? Inverse. So if volume is going down, pressure will go up. So what is the only thing pressure can do in this problem, ladies and gentlemen? It's got to go up. Now, there is a possibility. There is a chance that temperature could be trying to push pressure up. And volume could be trying to push it down. Which one wins? We don't know. We don't know. A tug of war between Christopher and Angel. Who wins?
None.
I got it.
You got the rope. I'm agreeing. I don't think either one of them could pick it up even. All right, so we're going to throw Shenza in with Christopher, okay? And we're going to throw Morgan in with Angel. Okay? Now who wins? I still don't know.
Yeah, I still say the word.
Until we actually see it happen, we don't know. Until we do the calculation. If you've got two variables that are trying to send this in opposite directions, it may not even change. It's possible that they could cancel each other out. Okay? So, how much time have I got? Oh, 4 minutes. Perfect. Perfect. Cross products are equal, ladies and gentlemen. Putting this all on one line. 105.3 kPa. 698 ml. 334.4 Kelvin. Equals P2, 421 milliliters, 288. .8 Kelvin. Solve it. I guess you guys are done. I guess you don't want the answer. Angle, can you solve that? Can you solve that? Steven, can you solve that? How would you do it, Steven? Multiplying what?
Oh my god, it's a big boy number. It's a big boy number.
Times 105
This is what I got.
times 698 times 334.
That's a humongous number.
Then what? Well, again, doing the same thing we just talked about, ladies and gentlemen. Isolating your
Oh yeah, you have to get it by yourself.
variable.
Oh yeah.
P2 is our variable. We isolate. Whoa, go back. We isolate it by dividing this side by 421 milliliter and 288.8 Kelvin. What you do to one side, look what happens to our units, ladies and gentlemen. What's the only unit we're left with?
Should be.
Hey, I will tell you this. I'm not done, so you're not leaving even if the bell rings until I get finished. The mistake that people make, they will do all of this work, all of it. And unless you know how to put this into your calculator so that it does the correct order of operations, you will still get this problem wrong. Because you have two numbers on the bottom here, you better make sure they are in parentheses when you divide by it and then multiply them together. Have a great day, ladies and gentlemen.